today I'll be going through this paper, Generalizing Plans to New Environments and Relational MDPs. This paper is by Carlos Gestrin, Daphne Koller, Chris Gerhardt, and Neil Kanodia. This is quite an old paper. It's from 2003. So the first thing to understand is in sequential decision-making tasks, these tasks are represented by something known as MDP or Markov decision processes, which are nothing but a tuple of state, action, rewards, and transitions. I'll make a separate video on what MDPs are, but for now, this is what MDP stands for, and you can look up a Wikipedia article on MDPs for a brief understanding. Anyways, the thing to know about MDPs is that for every task, the MDP would be different. Similarly, for every different configuration of an environment, the MDP would still be different. So let's say we have this game here where these are my army, this is my army, and these are my enemy, and I'm supposed to generate my army so as to attack the enemy later on. Now, even if I change the number of soldiers I have, the environment would be different. So this is very important to understand, because the algorithm now should understand that I have more resources or fewer resources and should optimize the way it tackles its attack accordingly. The problem that this paper is trying to solve is to come up with an approach to minimize replanning when similar instances of the environment are shown. So let's say the idea here for this domain is I have 5 such soldiers and 2 enemies, for example. And let's say there is another instance where I have, instead of 5, I have 10 soldiers and maybe 4 such enemy. Now, for humans, it's pretty trivial, right? You know, your strategy might not change that much. However, for algorithms and for planners, this is a lot different than the smaller case. Now, this problem is important, as the authors point out, because of 2 reasons. First is that it reduces replanning. So I don't have to plan again, because I can sort of reuse whatever I learned from my training set of environments. And the second more important reason, for me at least, is that when the environments get larger and larger, even the state-of-the-art planners might not work because the environments are so huge. Now, if the idea is that I can train on smaller instances and then be able to the learned behaviors in the smaller instances on the larger instances, then I would call it as we are able to generalize the plan successfully to newer or larger environments. So now let's talk about how the authors in this paper are dealing with this problem of reusing this notion of whatever we learned for some smaller domains into the larger instances of that domain. So one of the things I want to point out to somebody reading this paper is that the authors continuously use terms like scenarios and domains to refer to the same thing. What they're dealing with, at least in my opinion, is the environment is going to be the same, just that the configuration might change. The authors are presenting this novel idea of relational MDPs or RMDPs. Now the idea is that we will be thinking of this whole problem in an object-oriented view. So the domain would have objects, and those objects might belong to certain classes. So RMDP is sort of an extension of MDPs. So the whole idea is that the RMDP can represent the underlying MDP regardless of which world we choose. Let's see what RMDPs are. So as I said, an MDP is supposed to have 4 things: a state, action, a transition function, and the reward. The authors, they represent the domains as objects. So these objects can be something like peasants, a footman, gold for the game of freecraft. So these are objects, mind you. This is not the state, but these are objects. Now each of these objects can have certain attribute. For example, this peasant might have some task which can take the domain of waiting, mining, harvesting, building, and so on and so forth. This footman might have some task of killing the enemy, or the attribute that this is my enemy. And for something like the enemy, an attribute can be who is the footman that is trying to attack me. There is a peasant. It has 2 attributes. First is what task it can do and what health it can have. health has say 1, 2, 3 levels, and then task has 4 elements in the set. So the total combinations of the number of states this peasant can take are 12. This basically constitutes state of an object. These objects also have a relationship with other objects. So this is defined by the term links here. So let's say I have a peasant and it is working on barrack 1. So let's say there are several barracks being built, P1 and B2, and there are several peasants, P1, P2, P3. This peasant is working on barrack B1. So we can define a relationship between P1 and B1 such that P1 dot working on is B1. If the peasant is working on multiple such barracks, then maybe we can say B1 comma B2 and so on. So this is known as a link. It becomes quite apparent what the state space would be. The state space is this union of all the states of all of these objects. To take an action, an agent has to first decide which object it is going to take an action upon. So we have an agent and it has to give two things to take an action. First is what object it is going to take an action on, and the second is the action itself. So it's something like the agent can try to make a peasant P1 go and take some wood. So take wood is an action and the object is P1 here. So make note of this thing that the action is taken upon this object and not in the whole world. So all the objects come along with a description that, hey, I can only apply these 5 actions on P1. And the agent has to select an object and then the action. As we did with the state, the action of the RMDP would be the union of all the possible actions for all the possible objects. As we discussed, well, we know what the state S is, we know what the actions A are, and since the agent always has to pick an object first and then decide which action to take upon that object, it goes along the theory, simple RL theory, that the R of SA would look something like this, which is, well, as I said, each object belongs to a class. So let's say in the class of peasants, I choose P1, let's say peasants, I choose P1, and for P1, well, I have this particular state of P1 where my peasant is working on barrack B1 and it's trying to get wood from tree T1 and so on and so forth, and within that state I'm taking this action of get wood. So whatever the reward would be for taking this get wood action on this state, it goes here, and the total reward would then be summation for all such actions over all such objects which belong to all the given class. Now one more thing that remains is, what is this transition function T? The way the authors define this transition function is using dynamic Bayesian networks. Let's say I have this particular attribute and I want to decide, hey, what does this Px depend upon? So it's given by a Bayesian network here. There is a reason why they chose specifically DBNs. The reason is that they wanted the MDP to be factored. Now why did they want this? Is because the way they are trying to solve this MDP becomes intractable. They use something known as linear programming to solve this MDP. Now the state space is so huge in their case that this LP or linear programming solution is intractable. However, there is their previous work by Gestern, Kohler and Parr, which is able to efficiently perform the linear programming solution over the MDP when certain conditions are met, and those conditions include the MDP to be factored, which is why they go with this idea of using dynamic Bayesian networks for the MDP. So let's dive into this idea of how exactly are they going to come up with a policy. Remember, the way they are solving MDPs is via something known as linear programming. So it's basically you provide an objective you want to minimize and then you provide certain constraints. Now, even though their trick of efficiently solving factored MDPs using linear programming works well, they still have to reduce the exponential number of states. To give an example, as we saw, for each person P1 there exists 12 possible states. Let's say there are X number of such objects, then for each object there would be 12 states, which is 12 raised to power x number of states. So as we can see, the state space increases exponentially and can reach very large values very quickly with very small number of objects. And this of course becomes intractable even for linear programming with all sorts of tricks. So one of the ways they try to reduce this strain is using two observations or assumptions in their paper. The first assumption they make is that the value function of the task can be decomposed into linear combination of local value functions, which is given by equation 2. So as we know, the way we get a policy is by basically following from any state, taking an action A such that we maximize our value, or we can just pick the action that obtains the next state which has the maximum value. Now let's say we want to calculate value for this particular state where there are 2 enemies and 2 footmen. So for this, V2 cross 2 would involve all the factors like F1, E1, F2, E2. So the first assumption says that instead of using value functions which requires all possible combinations of all possible objects, we would approximate the global value function, which is this particular V, using the value function of individual objects, which is therefore this V is equal to V footman 1, V enemy 1, V footman 2 and V enemy 2. And it does not include something like V of footman 1, E1, V of footman 1, footman 2 and so on. It turns out it works pretty well, so they don't give why this assumption is valid. It's just that this is one of those assumptions which has been made for computational reasons and it works well. So the global value function denoted by VW or V omega or V of this world for a given state is basically the linear sum of all the value functions for each object in this world given by OW. So to put in context, this big O is the whole environment. This big O of W is a particular configuration of that environment known as a world. And then within it, there are this capital C, which is, well, within this world, this particular class is what we are talking about. And within this C, there can be small o's, which are basically objects. Now they know the global value function in terms of each and every object. They go one step beyond in generalizing this value function. Remember that I said that there is a notion of classes in this whole thing. We haven't used that concept up till now. So let's use it. So what happens is there is a world and there are classes like peasants, enemies or barracks and so on. For each class, there are several instances of that class like enemy 1, enemy 2, enemy 3 and so on and so forth. It's very similar to what we have in object-oriented programming. Now what happens is they make their second assumption at this point. Their assumption is that so this V of W right now depends upon all the objects. So rather than making it depend upon all the objects, we want to make V of W depend upon all the classes instead. So the way to do is just assume that all the objects, since they are there for the same purpose, like enemies, regardless of which enemy it is trying to defend itself from footmen. Or let's say there is a class footman, then regardless of which particular footman we are talking about, their goal would be to defeat some or the other enemy. So their total value function should be almost the same. Now the way to do is, as I said, is just assume that the value function of all the objects within this class is going to be the same. So instead of writing VW as a function of VO for all the objects, we write VW as a function of VCs for all the Cs for all the objects. The way they do it is given by equation 5, as in V of W is calculated by class, that is for each class, and within that class for each object. So these two summations are basically equivalent to our summation here. So for each class, for each object, I'll just use the VC for all the objects. So be it E1, E2 or E3, I'll still use V of E, V of E, V of E for all of these. Now, but you might ask, right, those objects would be in different situations. So let's say one of the footmen is dead and the other footman is alive. So their value functions must be different, right? The way they do it is that every footman has the same local value subfunction, but the dead guy would have a lower contribution. to do this, they say that these parameters play an essential role. Let's say value function for the footman is x plus y. So value of footman given x and y is x plus y. So for each footman, this is going to be the value function. Remember, we're talking about the function, not the value itself. However, the parameters might differ based on which footman we are talking about. So if the guy is dead, probably these xy values are going to be 0. For example, if x is health, then it's going to be 0, and then the value would decrease. On the other hand, if the guy is pretty healthy and active, the value would increase because the parameters are different. So the differentiating factors between the objects are the values of the parameters. However, that being said, the functions themselves are same for all of these objects. The authors in section 3 already defined an LP formulation for an MDP. Now we have already discussed the components of this RMDP: state, transition, action, and reward. We've also discussed how exactly we are going to get the value function for a given state in this RMDP using these two observations that I just talked about, and we get to something which is equation 5. Now we know all the components required to come up with a good policy. All that we need to do is basically fix this into another LP formulation that is given here, and we would get the answer. And remember, the idea of this paper is not to do all of these decompositions for an LP formulation to work, but rather the ideal situation would be that I am training my agent on some really small domains, and then magically whatever I learned from those small domains is applicable to the larger ones where I cannot even try to plan because it's so huge. So what they say is, let's say we won't sample the whole thing. So let's say there are 1000 possible configurations. We are going to sample only m such domains with some probability p of omega, which is given in this section here. Now they provide a guarantee here which basically says sampling m such samples is okay, in the sense that the final policy that I'm going to get is good enough and very close to the optimal policy. A brief discussion about this p of omega. One of the cool assumptions that these guys make is this, that let's say p of omega is the probability that we sample a particular type of domain for our learning phase. Now they assume that, well, let's say p of omega has a lot of objects. So let's say number of objects that this domain has is given by x. So as the number of objects increase, their function, their assumption here is that p of omega would decrease exponentially. So the probability of sampling that particular environment, which is very huge, becomes very small. This is good, right? Because the whole point of doing this work is for us to be able to generalize to larger versions. We weren't going to run our planners for the larger versions anyways. To provide some mathematical tractability, these guys are using these assumptions for this constraint here. Now that was RMDP. Now one of the last things that the authors do in this paper is this learning classes of objects. So let's say we have several objects, P1, P2, which belong to class P, and E1, E2, which belongs to class E. Now the previous assumption that they made is the value function of E1 and E2 are going to be the same, and P1 and P2 are going to be the same. However, there can be certain differences between these P1 and P2. Example that they give here in this text is, let's say only P1 has the ability to build barracks. This notion cannot be actually represented in this particular style of representing the domain. So the way they differentiate between P1 and P2 is via value functions. So instead of assuming that value function of P1 is more or less equal to value function of P2, what we'll do is we'll get for each object P1, P2, E1 and E2, we'll get some approximation of value function. Let's say here we get V1, here we get V2, here we get V3, here we get V4. So once we have it, let's say V1 and V3 are same and V2 and V4 are same. So instead of putting P1 and P2 have the same value function, what actually is the case is that P1 and E1 have the same value function, whereas P2 and E2 have the same value function. So we'll change our setting that all the objects of the same class have the same value function, and rather say that via this method, whatever we find, let's say we find this set of objects to have the same value function, from now on, once we're going to run our algorithm, will assume for the purpose of calculation of value function that they belong to the same class. So this trick is trying to relax the first primary assumption that the value functions of different objects that belong to the same class is the same. But rather what they say is, let's say we have a value function of different objects, regardless of which class they belong to. If they happen to have the same value function, then we're going to use them as such. They provide some evaluation on computer network administration domain. They don't provide a clear picture of what the problem here is, so I'll skip that part. However, a more illustrative example is this freecraft domain. The final results are pretty mixed, because on one hand they do say that they were able to generalize from smaller plans to slightly larger plans. On the other hand, they do say that when the domains become very big, they weren't able to do so. So some good points about this paper is, first being the probability thing that I talked about. As the number of objects increase, the probability of choosing that particular world decreases. The second thing I liked about this paper is that the way they build up RMDPs using DBNs and LPs as a previous result they had from their previous paper. I also like the running example of freecraft domain, which helps with the understanding of this paper. However, the thing I do not like is that the authors have a symbol in their formalization for literally everything, which makes the reading a bit more convoluted than the usual other papers that I have read. Overall, I think this is a good direction to generalize plan behaviors, because what we're attributing the behavior to is not the domain, but rather the objects of the domains, which can very well, and this is a valid assumption, that they can very well be present in the larger domains, but albeit in larger or different amounts. So this was my spiel on generalizing plans to new environments and relational MDPs. If you like the video, press like. If you want to look at other videos like these, press subscribe, and I'll talk to you guys in the next video. Thanks.